Welcome to the structure analysis class. So in this class, we will discuss about the cable subjected to uniform distribution load. So if you remember, last class we have started the cable analysis of cable structure. We have discussed how to analyze the cable structure if concentrated loads are acting, and at the end we have solved a problem also. So in this lecture, we'll more focus on the uniformly distributed load if it is acting on a cable. So this, so as if you remember last class we have discussed all the cable structure. Basically, if you consider a suspension bridge, that is actually a cable structure, right? There will be a cable which is taking the entire deck load of a structure. So if I just quickly draw a suspension bridge will be looking something like that. So you have two pier here, so both are maybe inside river, and this cable is connected somewhere here like that. Both the cables are fixed here, and then in the middle you have the bridge deck. So this one is bridge deck, and small cables are connected through bridge deck and the main suspension cable. So these cables are basically will take the entire load of a deck. So whatever load is coming from here, it will be transferred through these small cables, and these small cables again will transfer the load into the main cable. So this is our main bridge deck. So all the vehicles will be passing through this deck. So all the loads will be first transferred through this cable into this main cable, and then ultimately this main cable is grounded, so load will be transferred through the cable. So if you see, this cable is actually subjected to a distributed load, not only concentrated load, but these small cables are at a frequent interval it is placed. So this is a distributed load acting on a cable. So in that case, how the analysis will take place? How do you calculate the tension force in the cable in the different locations? So if you remember, in the last class we have discussed the cable under the concentrated load, where each segment of the cable carries the same load, but in a uniformly distributed load, here if you see, each point in a cable will, the tension force will vary, because the load here is a uniformly distributed load. So today first we'll derive our basic concepts, and then we'll solve a problems as well. So let's derive our basic problem. So just see here, this is a cable straight cable, one cable is connected into the two support. So this is one support, that is another support, and both the supports are hinge support. So if you recall, in the last class we have discussed hinge support has two unknown reactions. Similarly, here also you have the two unknowns. So 2 to 4 unknowns you have, and the cable's load also will vary, because this time loads are actually uniformly distributed load, right? W naught. So that's why the tension force in a cable will vary at every point because of the uniform UDL acting on it. So that's why we have to compute, or basically we have to we have to derive a tension equation for the tension force all along the cable, because in every point the tension force will be varying. So that actually we have to derive. So before deriving the tension force, first we have to find it out what could be the shape of the cable. So as I have discussed, uh, this is one support, and this side you have another hinge support, right? So originally, before applying any UDL into the cable will just tie it in the both the joints, right? Here will tie one end, there will be tied in another joint. So in that case, the length of the cable, I mean the cable will be straight. So after application of load, only the cable will become in a sag shape, right? So before application of UDL, the original the cable is straight. It is connected to these two joints. But once we apply UDL into the cable, so see the shape of the cable now changed. It earlier to a straight line. Now it is actually concave upward, right? So the change shape of the cable has changed. So to determine the tension force in a member, first we have to identify what is the shape of the cable, because that also now will vary. So let's derive first. So how to derive that? So what we have taken at a distance of x a small segment here. So if you see, this is a small segment which is at a distance of x from the left hand support. So this width of this small segment is delta x. Delta x means very small. We have computed very small amount length is there. So what we essentially did is we taken a section here, right? So small section, so left side and right side. So two small sections I have taken, and this middle part now drawn in a separately this free body diagram. So this small portion delta x is shown here. See delta x, and the tension in the cable will vary as I mentioned. So at every point in a cable, the tension force T will change. Unlike the last case where the load is concentrated, but here the load is UDL load. So one side of the segment, the load we considered, I mean the cable force is T, but the other side the T will be changed, right? So that's why we consider T plus delta T, because change in the tension force will be there. So each segment the forces are changing, right? So that's what we have kept, T plus delta T, and this side is T. And in this section UDL is acting W naught, so that's what W naught is acting. But if you replace UDL into a point load, then what will be the magnitude of the point load? So magnitude of the point load will be W naught is the UDL into distance, right? Force into how long it is acting. So entire length is delta x, so W naught into delta x is a concentrated load. Now we replaced this entire UDL, so this dotted line is basically the UDL. So we replaced UDL into a point load, and the magnitude of the point load is W naught into delta x. So where it will be acting from O, it will be acting at the middle, right? Middle of this total length. So total length we consider delta x. So middle will be delta x by 2. So at delta x by 2, this concentrated load is now acting. So this is our free body diagram, where left side is T force, right side there is change, increase, or there is a change basically in the tension force T plus delta T, and the concentrated load is acting. The force value is W naught into delta X, acting at a distance of delta X by 2. And the angle, so see this cable is basically the angle change is uniform, right? So left side, if the angle change is theta, then right side it is theta plus delta theta. There will be change in the angle as well. Then total linear distance we considered is the delta s. So this is now free body diagram. With this free body diagram, now let's derive our equations. So first we have to apply our summation of all the horizontal forces equal to 0. In the this free body diagram is also in the equilibrium, right? So if it is in equilibrium, then all the equilibrium equations are valid here. So what are the equilibrium equations? We have summation of all horizontal forces equal to 0, summation of all vertical forces equal to 0, and moment about any particular point, maybe for example O, should be equal to 0. So we have the three equilibrium of equations. So let's expand one by one. So first, let's see summation of all the horizontal forces equal to 0. So here in this free body diagram, what are the horizontal forces acting? So here this T force is acting, right? T force is an inclined force. So now it has two component. If we distribute, if we resolve it, one will be horizontal component, another will be vertical component. So let's do it. So T will have two component. One will be its horizontal component, this direction, and another will have the vertical component. So vertical component. So this component will be T cos theta, whereas vertical component will be T sine theta. So similarly, this T force also has two component, right? One is vertical component, another is horizontal component. So vertical component same. So this horizontal component will be cos theta plus delta theta. Similarly, vertical will be sine. So let's write the equation here. So first one is summation of all the horizontal forces equal to 0. So what are the horizontal forces acting? So first one is, if you see, t cos theta is acting left side, right? So left side we have, so this is the sign convention. Right side we consider it as a positive. If the load is going towards right side, then we consider it as a positive. So this t cos theta is going towards the left, right? So that's why it is minus t cos theta. Now here also you have t plus delta t. It's this force also has a horizontal component. So that is t plus delta t cos theta plus delta theta, which is going towards the right side. That's why it is a positive t plus delta t into cos theta plus delta theta equal to 0. So this, only these two forces are acting horizontally, so equal to 0. So that is first part is over. Now next is summation of all the vertical forces equal to 0. So let's do it first here. So you have what is sign convention? The right upside force we consider it as a positive, right? So this t sine theta, which is acting vertical component of t, which is acting downward, right? So that's why it is minus t sine theta. Now again you have this concentrated load is acting W naught delta x, which is also again downward. So that's why minus W naught into delta x. And then you have the horizontal component of this value, this t plus delta t, right? This is a vertical component. So vertical component will be t plus delta t sine theta plus delta theta, and which is acting upward, right? Upward means positive as per our sign convention. So that's why positive t plus delta t sine theta plus delta theta equal to 0. So this two equation is over. Now let's apply another moment equation. Summation of all the moments equal to 0. So see, the sign convention we considered anti-clockwise moment we consider it as a positive. So here is a O. So what are the forces acting towards O? So towards O, about O, how many forces are acting? So this T's horizontal component will be acting. Vertical component also will be creating moment. Similarly, for because of this force also will have moment. But because of these two forces, there won't be any moment because both the forces are passing through the point O, right? So let's first do it. What is the moment coming for this force? So t cos theta is acting in this direction, right? Anti-clockwise. So this side like that. So it is a clockwise direction. So t cos theta, and what is the height, distance from this point to O? So this height, vertical height. So vertical height we have considered is a delta y. So you have t cos theta and the distance is y. So which is clockwise direction, that's why it is negative, and t cos theta into delta y. So that's we have done for the one force. Now do it for this course, t sine theta. So t sine theta is acting anti-clockwise direction about O. If you draw, it is anti-clockwise, right? So anti-clockwise means positive. T sine theta into what is the distance from here to here? It is delta x. That's why delta x positive. So now these two forces over. Now we have another force, this concentrated force. So this force is also acting towards anti-clockwise, right? Towards anti-clockwise. So anti-clockwise means you have again positive, and what is the force? Force is W naught into WX, W naught into WX into distance from O. So it is delta x by 2. So that's what delta x by 2. So these are the three forces equal to 0. So these are the three equilibrium of equation just now we have derived. So now dividing each equation by delta x and taking a limit as delta x equal to 0, because see, delta x is very small, right? Very small segment here, delta x. So we can take a limit delta x tends to 0. Similarly, if you take delta x is 0 means what? Delta y also should go tends to 0. So delta y also tends to 0. Delta theta, change in angle also will be 0. Similarly, tension, change in tension force also tends to 0. So if you just take all the limits and if you divide it with delta x, ultimately you will get, this is the expression from first equation, you will get it. Similarly, if you do it for second equation and divide it by delta x, you will get it, this expression, right? You just divide it by delta x, divide it by delta x, only what W naught will be remains, right? So and that is, so these two equation you will get it. Now if you do it for third one, this one, you just divide it by delta x and delta y, you will get it dy dx equal to tan theta. So these three equations are actually derived using this equilibrium of equations. So now if you integrate, now first equation, this one, this equation, if you integrate, what will you get? T cos theta equal to some constant, right? If you integrate it, this equation. So at x equal to 0, so we considered our x from here, right? At x equal to 0 means what? We are here. So here, what will be T? T will be, T is what? Tension in the cable, right? At this x equal to 0, what is the T? T will be whatever force, reaction force is there, horizontal reaction force is there in this support. So that's what. So at x equal to 0, you will have the T equal to FH. So if you just substitute here, integrate and substitute, you will get it T cos theta equal to FH. So this is the equation, you will get it. Similarly, if you integrate this equation, what will you get? T sin theta equal to W naught into X, right? Just integrate it, just dx will come here. So you will get T sin theta equal to W naught EX. So T sin theta equal to W naught EX. So this is another equation. So this is one equation, this is another equation. You just divide it one by one. So T sin theta by T cos theta. So T will cancel out. So you will be getting tan theta equal to uh, tan theta equal to what? Dy dx. That's what we derived here. So dy dx equal to this by this, right? This by this. So W naught x by FH. That's what we did. Now this equation by this equation. So we will have right side also W naught x by FH. So you have this equation dy dx equal to W naught x by FH. So now if you take integration of this equation, what will you get? So you will get y equal to W naught x square by 2, right? If you take integration of W naught x by FH, so all are constant except x. So you will get W naught x square by 2 into FH. So W naught x square by FH. So you will get it this equation. If you integrate this equation. So now what will be there at y equal to at x equal to 0, x equal to 0 means at this point what is the height y, so y is 0, right? Y is the change in this height. So at x equal to 0 you will have y also 0. So if you just substitute here x equal to 0 equal, then y equal to 0, then you will get it fh equal to W naught and FH equal to, and another equation is like you have at x equal to entire length L, what is the y? Y is H, right? So if you just substitute y equal to H and x equal to L, then from here you will get FH equal to this equation. Let me do it quickly. So at x equal to, see this one I am talking, at x equal to this point. So at x equal to L, you have y equal to H. So just substitute this here in this equation. So from here you will get this equation. F equal to this one. Then just substitute F into main equation here FH, and you will get, this is our final equation. Y equal to H by L square into X square. So this is our final equation. So this Y is what? Y is the equation of this cable. So if you see y equal to h by L square into x square. So h is a constant, L also constant, length is constant, right? And x square is a variable. So basically this is the equation of a parabola. So that's why the shape of the cable will be always in a parabolic shape. So this is the equation of the cable, right? Y equal to this equation. So this is the equation of a parabola. So that's what we computed here. So whenever UDL is acting, please remember, very important equation we have derived just now. So whenever load is acting, whenever UDL is acting on a cable, the shape of the cable will be always parabolic. So this is the shape of the cable is parabolic. So now let's solve a problem quickly. So what is the question? Question tells a cable is shown in figure supports a girder. So this is a girder is actually suspended, right? This girder is actually suspended in a cable. So this is a cable and this girder is suspended. So whatever loads are there, all load girder load is actually transferred through these small cables into this main cable. So this main cable is actually subjected to a UDL because of this girder, maybe this girder carries the some load, vehicle load or something. So entire load is actually transferred through this cable to this main cable. So this main cable, now you can assume it is a UDL, uniformly distributed load. So you have to find it out, the tension at A, B and C. In these three locations you have to find it out what is the tension force T. That is our problem. So let's solve it quickly. So this is a actual diagram which is given to us. We have to find it out what is the tension force at A, tension force at B and what is the tension force at C. So we have just now derived this equation of this line. This is cable. So what was x? Always we considered x our coordinate, which will be the lowest point in a cable. So lowest point in a cable is at B, right? So this is our starting coordinate x. X will come this direction from here. So here x is 0, 0. So this side is positive x side and this side is negative x side. So this is the equation we have derived in the last slide, right? Y equal to W naught by 2fh into x square. So here few values are given. So W naught is the UDL, right? UDL is given to us, that is 850 pound per feet. So this value is given to us by 2FH. So substitute divided by 2, so 425. So this is our final equation of the cable, Y equal to this. Now assume the point C. Point C is located at a distance of x dash from the B. So this distance is x dash we considered. So now then what will be the y? So this is our equation, right? Equation of the cable. So here y will be here at this point, height is how much? 20. Now we are talking this location. So height is 20 equal to 425 by fh into x will be replaced by x star, x dash square. So from here you just compute what is fh. Fh will go just this is the equation we computed from this expression. So now if you write equation for about a, then a will be how much? So a is y is 40, so that's why 40 equal to equation 425 by fh into x square. So x is how much? So this is negative side of x, right? As I mentioned, x is here from starting from here, lowest point of the cable. So it is 0, 0. This side is positive side, this side is negative side. So I'm now writing equation with a. So that's why the negative sign, because I am going to minus x side. And what is this distance? So entire distance is given to us. Entire distance in the question is given 100 feet. So 100 feet minus x dash will be this distance. 100 minus x dash will be this distance. So that's what it is 100 minus x dash whole square. So from here also we'll get another equation. So if you solve two equation, this is one equation, this is another equation. So you will get it x dash equal to 4.41.42 feet. So x dash means at location at B, now we just computed. So location of B is 41.42 from this support. So this distance is 41.42. So now substitute x dash 41.42's value here and compute what is FH. FH is the horizontal thrust. So or a horizontal thrust FH, you just substitute it with the x dash value, you will get that much is the value of FH, right? So now find out what is dy dx. So dy dx will be, you just take dy dx. So dy dx will be 420. So 2 will come here, right? 850 by fh, substituted the value of fh and x. So this is a dy dx, like slope in the cable. So now what is at point A? So now if you compute what is the force at A, let's compute first what is the theta value. So at A, what is the value of x? At A, x value is 100 minus x dash. So x dash we just now computed. So what is x? X will be 100 minus x dash. X dash is this one. So x value is at A. I'm talking about at A. X value is minus 58.58. So substitute this value here, you will get dy dx. So to substitute this value here, we will get, this is the equation. So dy dx, which is basically tan theta A, is equal to this one. So from this equation, compute what is the value of theta A. Theta A is minus 53.79. So you just computed what is the value of theta A in this A location. Now simply find out now another equation we derived in the last slide, TA equal to FH by cos theta A. Theta A just now we derived. So find out what is cos theta A, and FH value also we derived, this 36459.2, and substitute you will get what is the value of TA. So TA is the tension at A, so that we have computed. So our main objective was to compute the tension at A, B and C. That is the question asked, to find out the tension at A, B and C. So at A we just computed. Now at B we have to compute. So what is the X? X, as I mentioned, starting point coordinate origin is at B, right? So X equal to 0 at B. So substitute X equal to 0, then dy dx will be also equal to 0. So tan theta B equal to dy dx equal to 0. So theta B also equal to 0. So in the same equation now, fh by cos theta b, instead of cos theta here it will be theta b, that will be tb. So that is 36 point at the end, by divided by cos 0 you will get some value. So there is the tension force at B. Now similarly at C, find out what is the theta value here. So here x equal to how much? X equal to x star, x dash value is 41.42, 41.42. So just find out what is the theta C. Theta C equal to 0.02331 into 41.42. So that's what 0.41 into 42. You got some value. So from here you calculate what is theta C. So once you know the value of theta C, just substitute this equation, Tc equal to fh by cos theta C. Same equation we are using every time. So from here substitute the value of cos theta Tc and you will get it final value. So like that we have to compute if a UDL is acting on a cable. So in the three different points we just computed whatever is the tension force. So now if I ask you what is the tension force at this point, just quickly you find out what is the distance from B to that point where you want to find it out. So once we know the x value here, substitute x value here, you get what is the value of theta. So once you know theta, find out fh by cos that theta, you will get the tension member at that particular location. So using this method, any location, basically you can find it out what is the tension force. So that's what. So in the last class we had discussed the how to analyze the cable when the concentrated force is acting, and in this lesson I discussed how to analyze the cable when the UDL is acting. So with these two lectures we are just completing the cables. So in the next lecture we'll discuss about the arches.